Experiment 7 is all about testing the pH of different samples. In this experiment, you'll be getting practice in using pH indicator paper and pH meters, which are two very common methods for measuring pHs. In this experiment, we'll be using a number of different chemical reagents, many of which you probably have at home in one form or another. While these reagents are relatively safe to work with, we still need you to look up the safety information for several of them. Please make sure to look up safety datasheets of the appropriate concentrations. In this experiment, you'll be given a number of samples, all of which are listed in this table, and you'll be asked to find the pH of those solutions using two different methods. The first method is using the indicator paper, and the second method is using a pH meter. Test those samples using the methods described in your lab manual or in the other videos in this playlist. And now we'll walk through that testing process for an example. You need to look at the left-hand column first to make sure that you're testing the correct sample. In this example, we're looking at 0.1 molar potassium carbonate. The first test that you'll do is the pH indicator paper test. So you'll test your sample by adding a drop of the sample to the pH paper. And remember that pH indicator paper can only be measured to whole number values. The next thing you'll do is you'll test the sample with a pH meter. So you'll immerse the probe and wait for the reading to stabilize. And for pH meters, you'll be recording a value with as many decimal places as the meter provides. And after you've done this, you're going to repeat the process for all of the samples. The final two columns in the table come into play when you start to answer the post-lab questions, specifically post-lab question 1. In the data table that you've been given, the structure column has been filled out for almost all of your samples. The structure column just represents the active ingredient in whatever sample that you're looking at. The only two samples that don't have a structure are tap water and distilled water. And when you get to the lab and you do your experiment, you're going to find that the pH for tap water and distilled water won't be neutral. That is, the pH won't be equal to 7. And some of the reasons for that will be explained by your instructor in the lab. The structure column for our potassium carbonate is just going to contain potassium carbonate. That is the structure that's going to be relevant when we're explaining the pH of this solution. The post-lab question tells you to write a net ionic equation that shows how the material produces either H plus or OH minus, so lowers the pH or raises the pH. And it specifies a net ionic equation because many of the materials that are listed in your table, many of the samples that you'll be testing, are salts. So when you add them to water, they dissociate, and there are often spectator ions that don't take part in the reactions. So we want you to write the equation that only shows the relevant bits of the reaction, that is, the net ionic equation. Acids are things that produce H plus ions when you add them to water. And in general, there will be two forms that you'll see for the net ionic equations for acids. And the first of those forms is the generic acid dissociation expression. You have an acid, HA, it dissociates to produce H plus and an anion. The other form for a net ionic equation producing H plus is the conjugate acid of a base, so BH plus, dissociating again to give you H plus and the conjugate base. And bases are things that produce OH minus when you add them to water. And the types of net ionic equation that you can get for bases producing OH minus are roughly similar to those for the acids. The first type you'll see is the reaction of a generic neutral base, B, with water. The base abstracts a proton from the water to make BH plus and OH minus. The second type is the reaction of a weak base in the form of an anion. The weak base reacts with water and abstracts a proton from the water, producing BH, a neutral material, and OH minus. A third way in which a base can produce OH minus can be seen in the case of metal hydroxides, where the metal hydroxide just dissociates and produces a metal cation and OH minus. In our example with potassium carbonate, Potassium carbonate is a salt, so when you add it to water, it will dissociate, and the potassium ions will be spectator ions that effectively don't influence the pH at all. So the reaction producing the OH- is the second reaction type that was mentioned, one with a negatively charged ion reacting with water. We have the carbonate ion, a 2- ion, reacting with water to produce the HCO3- ion, the bicarbonate ion, which has a single negative charge. The charge has been increased from -2 to -1 because that proton, that positively charged ion, has been added. And what's left of the water is the OH- ion, the hydroxide ion that raises the pH of this solution. The second post-lab question asks you to develop a list of pros and cons for using pH paper and pH meters. And when you're making this list of pros and cons for the two different methods, remember that you are in a laboratory course, which is inherently practical. So not only do you need to think about things like measurement, precision, and reliability, you also need to make very practical considerations like portability and cost and training requirements and things like this.